Hi. Hi, welcome to 441. More stuff again. This time we are going to do a full fatigue evaluation of a particular part. So we are going to see everything. Okay, how to do all the calculations, how to draw free body diagrams, how to calculate the fatigue stress concentration factors, figure out how safe it is or what life it has and all of that. Our example is a disc sander. You know what that is? So it's a disc like this. In this case, this is the housing. That's the disc. And what it is doing is it is smoothing out the edge of this table. You see that? It's going to spin around like that. Oops. So it's going to spin around like that and it's going to slowly smoothen out the table. Typically speaking, if you are here, oops, sorry. So if you are in the periphery here, somewhere here, you will be applying a large torque to the motor. And your most critical situation, if you want to evaluate whether it's going to survive in fatigue or not, you're going to push something against it, right? And when you push something against it and then it turns fast, you will develop a torque and then bending and all kinds of things, and you have to figure out how long it will last, how safe it is, and so on. Okay, so this is what a disc sander is. Now of course we are going to show a picture of a disc sander, and that's going to look like this. So you got the idea, right? So the picture of a disc sander, look sideways is this. This is the disc, this is the housing. This is the housing. Let's go up here, let's make it. So in reality there will be some curve here, and inside this there will be a shaft that goes in like that. You see what I mean? And things happen here. So we are only interested in this region. Can you see that? And this is supposed to be very thin, so there's not much bending here. Most of the bending, the critical location for bending is here. Okay, so we are worried about whether or not it will last. So the first step to doing this, estimate external load. This is a hard problem. You know, this is not an easy thing. So what do you think is going to happen? You're going to, the worst case scenario, so try worst case. So what happens is you are going to push here like that. That's the piece, that is F1. You're going to push against it, okay? Hard enough. So if you do that, what will happen is because of friction, you will get a sideways force, F side. That's the frictional force. This thing is rotating like that. And we are going to assume friction force is enough to almost stall the motor. Right, so you're pushing it so hard that it's going to stall the motor. This is an extreme case. This is not what is going to happen. But we are going to look at the extreme case and see how safe it is. Okay. So it's almost going to stall the motor. And if you look at this particular motor stalling torque is what you have to look up. So you go look up the specifications for the motor, and it turns out the motor stalling torque is about 12 Newton meters. Okay. That's good. And the size from here to here is about 100 mm. That's excellent. So you already know. So first step is F sideways equal to 12 Newton meter divided by 100 millimeters, which is 12,000 divided by 100, which is 120 newtons. That's the sideways force. Excellent. Now, what about F1? You agree that the motor is just running, right? So yeah, so we know that Fs must be equal to mu times F1. This is sliding friction. This is where again your knowledge of 221 comes in. Okay, so look at how we are estimating the load. We just assume some worst case, and we got some basic information, and we backed out everything else. Okay, we are not done yet. So I have to guess mu. You can run some test. Or look it up, and you will find that mu is about 0.6. Very high friction. This is one of the highest frictions. So immediately you will find that F1 is 120 over 0.6, which is 20 over 0.1, which is 200 newtons. See, now we got everything that we needed. External load is known. So F1 is 200 newtons. Fs is 120 newtons. You see that? All of this you have to do. This is the external load analysis. Step 2. We are going to look at material fatigue analysis. Okay, so you know what to start with, right? So I need to know. So I am going to do this in Excel so that you can see all the calculations. So let's see, where is that thing? Okay, there you go. So I'm going to blow it up a little bit so that you can see better. So material fatigue analysis starts out with S ultimate, and I have to look this up. There is no other way. So you go find out what the bar material is made of, and you figure out what it is, and it is given to us as 900 megapascals. And then we can look up SY, turns out to be 750 megapascals. Sometimes this itself is an issue and you have to find it out. So immediately its ideal endurance limit, SE prime, is equal to 0.5 times that, 450 megapascals. This is easy, right? Because this is less than 1400, so we are okay. Similarly, if you want to look up, we can look up SF, which is the 10 to the 3. This is the short life fatigue, and for this you have to look up F times SUT. So I'm going to write it as, and that turns out to be equal to 900 times, you know where to look for F, right? And it turns out to be about 900 times 0.85, which is 765 megapascals. Okay, so if you have this, then the next thing is to find the actual limit. This is ideal. So let us make sure we know what these things are. This is tensile strength. This is yield strength. This is 10 to the 3 cycle limit. Now I have to calculate. Now we got to start calculating the actual endurance. You know, we got to do all these factors, right? So first thing is I need to know something about surface finish, and you can guess we are going to assume it's a machined surface. Dimension, so immediately that will tell me K surf turns out to be 0.74. Remember, this yield strength is high, right? So K surf will be actually be very sensitive to surface finish. Okay, so that's K surf. Then we want to say size effect. So I need to know the dimension, diameter.